All right, well, let's just get started then. Well, welcome everyone. This is a special event hosted by AILA during the Innovate Pasadena Connect week. And so today, if you don't know anything about AILA, we're a nonprofit organization based here in Los Angeles, focusing on accelerating innovation for social good. And so through media and events, we convene people to have these interesting conversations. And so tonight is a really special night. That's where we get to have Dr. Wei Gao from Caltech, Dr. Tim Mullen from Intheon, and then Yiwen Li from Masimo here to have a conversation. So first off, what we're going to do is have Dr. Wei Gao give a presentation on his work developing reliable sensors. Then after that, we'll go into a presentation with Dr. Tim Mullen talking about brain-computer interfaces and AI. Then afterwards, Yiwen Li will moderate a fireside chat between the two. And if you have any questions, please just drop them in the chat and we'll get to them afterwards. But without further ado, Dr. Wei Gao will be presenting first. So please keep your mics and your cameras off. And again, please use the chat to communicate with us. All right, enjoy.
Thanks, Todd, for the introduction and for the opportunity. And hi, everyone. It's wonderful to be here virtually to share our recent research on skin interface wearable biosensors. I'm Wei Gao. I'm an assistant professor of medical engineering at Caltech. So my lab mainly around 30 people right now. We mainly developing wearable biosensors for personalized healthcare. As we know, wearables can play a very important role in personalized healthcare because they can continuously collect data from our body and tell us what's going on and what's going wrong with our health. But if you look at all these commercially available wearable health monitors, like Apple Watch, Fitbit, or different kind of like a smart band, as you can see, they can mainly track the physical activities or vital signs. For example, they can monitor how many steps you walked and what is your heart rate. Even recently, some small smartwatch such as Apple Watch can do EKG, but still they're limited to the physical parameters. So they cannot provide more useful information about our health at the molecular level. So we think a major gap, which is also a great opportunity for research in wearable biosensors, is how can we develop this wearable biosensors that can monitor, that can perform physiological monitoring at the molecular level, ideally non-invasively. We know that right now we have CGM, continuous glucose monitor, that can continuously collect glucose level, but still it is invasive. How can we non-invasively track the biomarker level from our body? So we are looking at one important body fluid, human sweat. Sweat, we are sweating all the time. Sweat contains many important biomarkers, and it can be retrieved continuously, conveniently, and non-invasively. And we can identify different types of analytes, including electrolytes, such as sodium, chloride, potassium, pH. We can also find different types of metabolites, including lactic acid, glucose, urea, uric acid, creatinine. Basically, over 30 amino acids and over 300 proteins were found in human sweat. We can also see various substances such as heavy metals, drugs, and alcohols. Imagine that if we could develop a wearable sensor platform, we can real-time analyzing this biomarker from the skin. We could non-invasive monitor our health. Basically, we can continuously collect large set of chemical information from our daily activities. And we could use this type of device or technology for fitness tracking, like a Fitbit, but do chemical molecular monitoring. We can also use this for disease diagnosis and health monitoring. And very importantly, this large set of chemical information is not previously accessible. So this is the enabling technology. This large set of chemical information collection, if we couple this with a large set of physical information we collected, and you run big data analysis, machine learning, which is today's topic, we can enable numerous fundamental and clinical investigations, especially such wearable technology can play a crucial role in preventive care, identify the risks and potential issue early for timely intervention. So around almost 7 years ago, I published my first work we developed a fully integrated wearable sweat sensing platform that can perform in situ multiplex sweat analysis. So this wearable sensor can real-time analyze metabolites, including glucose and lactate, electrolytes such as sodium and potassium, as well as skin temperature. The fully integrated system can perform on-site signal conditioning, processing, and wireless transmission. So you can imagine this is a smartwatch, but it's a chemical sensing capability. The entire system is flexible. We can replace the sensing electrode. It's a disposable electrode very easily, and the whole electronic part is reusable. And all the data collected by these chemical sensors can be wirelessly sent to cell phones through Bluetooth. And we also developed the cell phone app. We have both Android and iOS version, can real-time display the biomarker information on the phone. Here are some information we collected during the vigorous exercise, for example. Because we are developing wearables, we want our wearables to have high performance and low cost for consumer use, right? That's why recently we tried to develop a mass-producible approach to fabricate a high-performance chemical sensor. Previously, if you want to detect the low concentration biomarkers in our body fluid, we need to use some nanotechnology or nanomaterials. Basically, you mix the nanomaterial into a cocktail, and you can drop cast on each electrode. You immobilize each sensor. As you can imagine, it's manual preparation, larger sensor variation, and higher level costs. We recently developed a CO2 laser engraved lab on the skin. Basically, this sensor patch is a microfluidic sensor patch that can perform chemical sensing to analyzing biomarkers in sweat. It can also perform physical sensing to monitor the vital signs such as respiration and heart rate. So the entire system can be made by CO2. Why? Because carbon dioxide, the laser engraving, if we use polyimide, the plastic is polyimide as substrate. This laser will burn in the surface of polyimide to fabricate this beautiful graphene structure. And the graphene, has very good performance, electrochemical performance, and high surface area. So we can control laser parameters to control the morphology and property of graphene. Based on this, we can design high performance physical sensor and high performance chemical sensor. And we can also use a laser to cut microfluidics. Why we need the microfluidics? Imagine that if you are analyzing sweat, what if sweat evaporates, right? What happens if new sweat comes out mixed with old sweat? That's why we designed this microfluidics. The sensor is sitting inside the reservoir. They don't really have contact with the skin, also for safety reason. So when sweat comes out, it will push away the old sweat. And all the time, basically, the sensor will analyze their fresh sweat. And we have minimized the influence from sweat evaporation as well. As I said, the entire microfluidic multimodal sensor patch can be prepared simply using a CO2 laser engraving. So the lead author, our female graduate student, Isabella, who also recently received the Forbes 30 under 30 in science. So our lab is not only developing sensor patch, we also want to make sure we can collect the reliable data. That's why all our work involves system integration. From chemistry material from scratch, we build a biosensor and we build the fully integrated system to collect this data using cell phone. Here, we package our sensor into wristband, headband. It could be a bandage-like sensor patch can be attached onto different body parts. So we can continuously collect data during the physical activities. And we also validated our sensor reading or accuracy using the gold standards, such as mass spectrum, ELISA kits, to make sure we can read the biomarker level reliably and accurately. So till now, some people may have a question. Since you're doing sweat analysis, what if I don't have sweat? Right? Like many people don't sweat much, even when they do exercise. So we have to address this problem. How can we access sweat beyond exercise? What if, can you do sweat analysis while I'm doing office work? Can you do sweat analysis while the person is during the sleeping, in fact? Yeah, the answer is yes. So we actually proposed a new platform. Basically, it is a wearable system that can perform on-demand sweat extraction and sensing. So basically, the entire system can be controlled by the cell phone app. If we want to sweat analysis, first we want to extract sweat, right? Especially for many clinical studies, as you can imagine, many patients that cannot do vigorous exercise, right? Right now, we can just need a click button from a cell phone. We can apply a small current through the skin and to deliver drug molecules below the sweat gland, basically below the skin to stimulate the sweat gland. So these drug molecules can trigger local sweating. You only sweat from this small area, and you only need to apply this current for a few minutes, and the sweating process can last from hours to even days, only from this small area. And our sensor patch is here to they can real-time perform sweat analysis. So these actually allow us to do many biomedical applications, even in a clinical setting, right? I want to show you some examples. Firstly, disease diagnosis. A well-known application for sweat test is cystic fibrosis diagnosis. Cystic fibrosis is a genetic lung disease. Clinically, the diagnosis is based on sweat chloride. The doctor will collect sweat, send out in the laboratory to perform equipment analysis. After several days or a week, they can receive the data, which is based on sweat chloride for this CF diagnosis. In collaboration with the Stanford Cystic Fibrosis Center, we actually evaluated our sensor to perform on-demand sweat extraction and chloride sensing. And basically only need 20 to 25 minutes so we can reliably analyzing the sodium chloride level in our body, in our sweat in this case. And as you can see, for the CF patients, their sodium chloride level are much higher compared to healthy people. And we can, based on this, we can say our device can be used for screening and diagnosing cystic fibrosis. To look beyond that, can we do the metabolic monitoring? Another example we recently demonstrated is gout management. Gout, is the most common inflammatory arthritis affecting tens of millions of people around the world. Gout is characterized by hyperuricemia, basically the high uric acid level in our body crystallized near the joint, and that will trigger a gout attack, tremendous pain. My brother has gout as well. And many people developing gout either because of a genetic reason or because of lifestyle. So if we could monitor uric acid level, it's very important for healthy people to really minimize the chance, change lifestyle, minimize chance for developing gout. For gout patients, it will help them to really avoid or minimize the chance to get a gout attack. And for gout patients on medication, it will help them to personalize their drug doses to make sure they can maintain uric acid level at a healthy range. So we applied our laser engraved this sensor patch to monitor uric acid on healthy people. You see male, female. We found that during the fasting period, after intake some purine-rich food, which could be a can of sardine, for example, we see that blood uric acid and sweat uric acid show a very similar pattern. And after this dietary intake, we see increase of uric acid in both sweat and blood. In collaboration with the UCLA Medical Center, basically we work with Dr. Yiwen Li, who is the chief of clinical nutrition at UCLA. We recruited patients with gout and subject with hyperuricemia. We found that for the patients with gout, they have high uric acid in both serum and the sweat, much higher compared to healthy people. And if we track one subject for 7 hours during the day, we found that sweat follow closely to serum uric acid level. And we obtained a correlation factor of around 0.864 between sweat and serum uric acid. Right now, we are working together to monitor a number of nutrients and metabolites, including amino acid, vitamin, many biomarkers in collaboration with the UCLA Medical Center. We want to identify the metabolic risk factors, especially toward the metabolic syndrome monitoring, which could be a risk factor for most severe health conditions. Metabolic syndrome is already affecting 1/3 of the US adult population. Another important application is how can we use this telemedicine biosensor for monitor stress and mental health. Right now, 95% of the diseases, they are stress related. And because of COVID-19, people suffer more from mental disorders. There's like 260 million people had major depressive disorder. 6 to 9% of US adults has PTSD. But right now, all these stress and mental health conditions, the gold standard for diagnosing, basically they're based on questionnaires. you get filled out some questionnaire, get some score. As you can imagine, such questionnaire could be very subjective, right? How can we quantify stress? And we are looking for biosensor that can accurately monitor stress level. Of course, one of the most well-known biomarker will be stress hormone, cortisol. So, but if you draw blood to monitor cortisol level, the blood draw itself is stress inducing. That's why, which is not very good, right? If you want to monitor stress by introducing stress, which is not good. That's why we try to do non-invasive stress hormone monitoring. By using our laser engraved graphene sensor patch, we developed this cortisol sensor that can quantify cortisol level very quickly, within 1.5 minutes, in fact. And in this case, this biosensor can perform rapid and accurate analysis. It works in sweat, saliva, buffer, and we also validated our sensor is gold standard ELISA. And we found that sweat, saliva, and blood cortisol level show very similar pattern, although the absolute concentration in sweat and saliva are much lower compared to serum. And morning cortisol level is always higher than afternoon, which is in agreement with the circadian rhythm. Cortisol level, not only level is important, the pattern of cortisol is also very important. Every day, our typical cortisol level is morning very high, afternoon or evening very low. Every day follows such a circadian rhythm. The circadian pattern of cortisol is related to different health conditions. People with depression, PTSD, their pattern, the cortisol pattern is different from healthy people. And we also identify that we can actually see the circadian rhythm of cortisol in human sweat, not only blood. We also identify this phenomenon in human sweat. And we also obtain a high correlation between sweat and serum cortisol level. And to further evaluate, can we use this to monitor stress response, right? We apply different stressors. For example, excuse me. Okay, first the stressor we applied is aerobic exercise, which vigorous exercise is a stressor, let people feel stress. And we found that during the exercise, the cortisol level increased very quickly. And of course, the exercise induced sweat as well. If we don't have sweat, typically, right, we can use anaphylaxis, as I said, as a way we have the integrated system that can induce sweat. That's why we did another stressor, cold pressure test. Basically, put the hand into ice water, you will feel a lot of pain and stress. In this case, we also identified the stress hormone level increased rapidly in human sweat using our sensor. Right now, we are working with NASA, with Navy to apply our wearable sensor to monitor the human performance of the astronauts and warfighters. So just one more slide here on sensors. It's not about a sweat test. With similar sweat sensing technology, we developed a multiplex telemedicine sensor platform for COVID-19 diagnosis. We call it the SARS-CoV-2 rapidplex. It's still, again, based on our laser engraved graphene biosensor. We developed this rapidplex that is mass producible, low cost, and they can simultaneously monitor virus antigen, virus antibody, and inflammatory biomarkers. Based on this, we can get a 3-aspect information. Basically, from virus antigen, we know whether we are currently infected. From virus antibody, we know our immunity information, whether we get infected before or our vaccine status. And from inflammatory biomarker level, we know how severe our infection is. Basically, we can get all these within 10 minutes in both saliva and blood. We actually validated the sensors, the sensitivity against, MERS, selectivity against SARS and MERS. We also validated our sensing accuracy in COVID-19 positive and negative patient samples. We found that for the COVID positive samples, we obtain all high level compared to healthy people. We can differentiate all the samples from patients and from healthy subjects. So the last part of my talk, I want to briefly mention how can we power our future wearables. I showed some technology. We can continuously collect data from our body for health monitoring, but how can we power them? Right now we are using lithium battery, but battery need to be recharged, right? It's not everywhere the electricity is chargeable or available for recharging. So ideally, the future wearables could harvest energy from either the environment or from the human body. Since we are doing sweat tests, sweat analysis, one idea coming to our mind, can we use sweat to power our sweat sensor? So basically, we developed this battery-free system that can entirely powered by lactic acid, this chemical in human sweat using biofuel cells. We can convert this sweat chemical into electricity. And the entire system, we get in high enough power, they can power multiple biosensor, electronic circuitry, and Bluetooth communication without using any battery. So how we can achieve that? We're using actually very interesting materials from 0-dimensional to 3-dimensional material to increase electrocatalytic surface area by 3,000 times. We obtain very high power from raw human sweat, 2 to 3 milliwatt per centimeter square. We can get continuously this power, which is high enough to make this happen. We develop this soft, fully packaged system without using any battery. As I said, we can continuously monitor glucose, pH, urea, and ammonia from vigorous exercise here. We in collaboration with another Caltech professor, Professor Azita Imami, we actually developed this miniaturized system. You see, Professor Imami is an IC design expert. We can put the entire electronic module to be very small, 1 by 1.3 millimeter. The entire packaged system is only 7 millimeter by 7 millimeter. They can provide a stable power output still. As you can imagine, we can miniaturize our future wearable sensor. The last slide on research is we can not only power our wearables using biofuel, we can also power the wearables using our body motion. So we developed this also, again, battery-free system that can harvest energy using a flexible primitive PCB based freestanding triple electrical nano generator. We can convert mechanical deformation, mechanical motion into electricity. And we get enough power from human body motion that we can power multiple sensors, electronic circuitry, and Bluetooth communication without using battery. In the end, I want to summarize, we developed this system that can real-time monitor a number of different types of biomarkers in human sweat. We continuously collect data from people's daily activity. This could be used or enable many applications in fitness tracking, disease diagnosis, and very importantly, new investigations toward preventive care. And I would like to thank my team at Caltech. Right now, we have actually replaced the new photo. We have over 30 researchers in my team. And of course, our collaborators on the technology development and clinical studies. And also very important, our funding support. Thank you very much for all your attention. I'll be happy to take any question later on. Thank you.
Okay, I will jump right in and speak on machine learning powered brain-computer interface technologies. So my name's Tim Mullen, and I'm CEO at Intheon. And at Intheon, we are pioneering a ecosystem that's aimed at democratizing access to neurotechnology. So I'm going to just give an overview here about some of the machine learning powered approaches to BCI development and design and applications in the real world. So first, I'm going to give you a little primer on brain-computer interfaces. And what's important to recognize is that in recent decades, we've seen a number of different neurotech advances that are allowing us to see into the brain and to record and change brain structure at really unprecedented resolution. And at the same time, we're seeing advances in computing power and machine learning and AI. And those are enabling us to process and decode vast quantities of neural data and identify mental states. So really the convergence of these two fields is at the heart of this rapidly growing field of BCIs. So what is a brain-computer interface? Well, the formal definition of a BCI is any system that measures central nervous system activity and then converts it into an artificial output that replaces, restores, enhances, supplements, or improves natural CNS output. And in doing so, it then changes the ongoing interactions between the central nervous system and its external or internal environment. And this has also been extended to include other non-brain neural inputs like eye tracking or the peripheral nervous system. And feature extraction and feature translation are two key components here that rely on machine learning and AI. And this typically involves translating neural and physiological signals into measures of one's mental state. So these are some of the kinds of mental states that are typically of interest, and that includes intended movement, imagined speech, mental focus, alertness, stress, relaxation, mood, emotional valence, and many others. So here I've shown a categorization of current and emerging neural interface hardware for reading and writing to the brain. And one thing to note here is that as hardware penetrates deeper into the body, we generally get increased measurement precision, but also the greater the risk and complications of implanting and removing hardware, and the greater the data processing and bandwidth burdens. So there's a trade-off here to consider. Here I've shown some of the major non-invasive modalities. Most of the non-clinical BCI applications today use non-invasive technology. So this includes output or read interfaces and input or write interfaces. And these can be realized in different form factors like head or clothing wearables or eyewear, also head-mounted displays, hearables, which are sensors in or around the ear, body wearables, even epidermal tattoos, subepithelial or subcutaneous embedded implants. Most BCIs rely on data from the central or peripheral nervous system, but also like what Professor Wei Gao was talking about earlier, with body wearables that might record chemical biomarkers such as hormones or metabolite levels. These also could be useful for providing context in decoding mental states or direct information useful for a decoder. These here are a few of the commercially available EEG systems and platforms. EEG is electroencephalography, records brain waves basically. And the important thing to note is that research grade systems, which are shown on the left here, typically have 64 to 128 electrodes, but are big and bulky. And then as consumer devices become more wearable, they typically have fewer electrodes. And that reduces the amount of information they can extract and their range of applications. So the neuroimaging applications like source localization and such, they can require like 16 to 64 electrodes. So an important milestone for commercial application is really wearable, lightweight systems with many electrodes. Mark Weiser, who is the father of ubiquitous computing, he famously said that the most profound technologies are those that disappear, that weave themselves into the fabric of everyday life until they are indistinguishable from it. And this is becoming true for BCIs. So the image on the left shows Jacques Vidal's BCI system from 1973, which occupied an entire room. And now today, thanks to advances in hardware miniaturization, embedded processing, cloud computing, these same capabilities and more are achieved by tech that can fit in your hand or be worn on your body. So the tech is really disappearing, becoming more ubiquitous. Here, I'm just showing an example of this where this person is wearing a brain sensor inside her ear, and it's streaming data to the cloud and decoding her neural state using Intheon's Neuroscale platform.
Alexa, ask Neuroscale for my average relaxation level over the last 5 minutes.
Let's hold it up so she can respond.
Your average relaxation level over the last 5 minutes was 36%. Not bad, but maybe you want to try taking a little break?
So what she was doing there was interacting with a distributed cloud system, Alexa, where Alexa was able to have information about her state, namely her relaxation state, and then do something useful with that information, provide her some information about that. So this is an example of how connecting brain-computer interface technologies to the Internet of Things is creating new possibilities for how we interact with the world. What we're going to see in the coming decades is a transition from wearable devices to implanted BCIs. And at this point, they're basically going to disappear altogether as they become essentially woven seamlessly into our bodies. This is closer to the sort of stuff that Professor Gao was talking about. There are many different current and emerging applications of BCI tech. And what I've shown here are assistive technologies for communication or motor function, augmented cognition and accelerated learning applications, or systems that give deeper insight into some of our cognitive and brain health and well-being factors, sort of Fitbit for the mind that's shown on the upper right here. And one of the most promising uses of BCI tech is to restore or enhance brain function, primarily through targeted neurofeedback or energetic neuromodulation. And then finally, BCIs can be used to enrich human creativity and aesthetics, enable new experiences and art forms. And these were actually some of the earliest uses of BCI technology. One interesting fact is that in the US alone, there's more than 11 million patients that could benefit from an advanced BCI. But with that said, the long-term impact really extends far beyond just clinical applications and into nearly every area of transformative tech for thriving and well-being. So now I'm going to talk a bit about brain state decoding using machine learning and AI specifically. And first, let me just show you this. This is a list of 5 key opportunities for advancing machine learning driven brain computer interface technologies. And the first is really the ability to measure brain body behavior context data unobtrusively. So these are like wearables and things like this. Secondly, to be able to apply robust signal processing and multimodal machine learning and AI for mental state identification from different types of data sources. 3, the ability to generalize models using large-scale heterogeneous data. So it's not big data type of problems. 4, the ability to adapt models to individual physiology and context. And then finally, having standards and platforms that enable rapid deployment of user-facing applications using state-of-the-art validated BCI tech, and really having strong ethics built into the foundation of our technology as well. You know, we want to make technology that is really supporting human flourishing and supporting human rights. So here are some of the typical machine learning and AI approaches for BCI. And the conventional approaches typically combine feature extraction with statistical machine learning for classification. And some of the typical neural features here include things like spectral power, evoked potentials, population vector coding, hemodynamic signals. The supervised feature learning methods tend to use labeled training data to learn features that discriminate well between different classes. And then the unsupervised methods typically learn features that are maximally uncorrelated or independent of each other, or which tend to maximize signal to noise. So for classification, we can distinguish between the machine learning and the deep learning approaches. And the workhorses of machine learning here in BCIs are basically generalized linear models, which broadly speaking include many linear and nonlinear regression models, SVMs, even things like linear discriminant analyses can fit in this category, broadly speaking. The deep learning methods include various kinds of like convolutional neural networks that accommodate spatiotemporal neural representations. And a popular ConvNet approach for EEG data, popular CNN there is a EEGNet. And that works particularly well for oscillatory or evoked response data. Transformer models and other sequence learning methods are also recently being applied with pretty good success. And then cross-cutting over these methods, over these different categories, we have pre-processing and artifact removal methods, methods for denoising, regularization techniques that impose different prior assumptions on the data, usually improve performance under limited data or noisy conditions, which is basically the norm for BCI technology. You're often in a data impoverished space. Then data augmentation methods that can be kind of seen as a form of regularization, multitask learning, which can improve model generalization and also enable fusion of different kinds of data. And transfer learning is also a powerful approach for model generalization across individuals or tasks. So fortunately, you don't need to implement all of these machine learning and data access methods yourself from scratch. There's several BCI software resources you can use to get started. That includes things like Neuropipe, BCI Lab, Lab Streaming Layer. These are team members at Intheon have developed and or maintain, as well as like OpenVibe, which is developed at INRIA. And at Intheon, our middleware platform is designed to enable data acquisition from numerous sensor devices and file formats, and then apply a full stack of data analytics, which ranges from cleaning and signal processing through training BCI models, through visualization and report generation, and then provide the results to diverse end user applications. There's two main software platforms here, Neuropipe and Neuroscale. And with the Neuropipe suite, you can design and run bioneural data processing and BCI pipelines using hundreds of pre-built or custom modules in Python. And then with Neuroscale, you can upload or stream your data to the cloud, deploy turnkey and customizable Neuropipe workflows, and then access the results in real time or batch on any internet connected device. Typically, this is done using either like a web interface or an API. So this here is an example of a typical BCI task where a user is imagining left and right movements, and what you can hear the left, now you can see the bar going up on the left. When you hear right, the bar goes up on the right. And this sort of decoder can be used as a control signal for a device, for instance, say like a quadcopter or a wheelchair. And if we want to build a pipeline for achieving this using the Neuropipe suite, we can do it without needing to actually write any code. So we can use the pipeline designer to say, add a node that acquires real-time data via LSL, then adds a bandpass filter here to clean up the data. We can plot the result of that. So now we see some time series data from the EEG sensors. We then can segment the data, which basically chops out little chunks of data around particular events of interest, give that to a common spatial patterns feature extractor, and then a logistic regression classifier. And then here we inject some calibration data. That's generally data collected maybe like 20 minutes of a person imagining left, imagining right, multiple times. And we now can inject that data into our classification stream. And that allows us now to wire up a real time data input, and it will calibrate and train a model in real time. And now what's coming out here are the probabilities of you imagining left or imagining right. And you can use that then to, for instance, control one of your devices. So you can also build pipelines using Python in a script environment. And here the code on the left is basically equivalent to the pipeline on the right. In fact, it is exactly the same. And you can also create your own data processing nodes in Python. You can mix and match them with any of the hundreds of Ntheon's pre-built nodes. You can also work with Neuropipe procedurally as a function library within your Jupyter notebook or your favorite Python programming environment. And that allows you to like mix and match Neuropipe processing components with your own code or your own data science libraries. So this example here is a Unity 3D environment that's using Neuropipe under the hood for real-time computation of EEG brain activity, physiometrics like heart rate, and closed-loop BCI. And you can put on a commercial EEG system and actually fly to a part of your brain and observe and control your own brain and heart activity in real time. That's all powered by Neuropipe. And any Neuropipe pipeline can run on the Neuroscale Cloud platform. And that allows access to powerful BCI capability from any internet connected device. So for instance, in this example, brain networks associated with meditative concentration are used to drive this augmented reality neurofeedback mobile app. The Intheon platform also supports lots of different kinds of hardware devices and software interfaces. This is in part through the open source lab streaming layer project that I mentioned earlier. And LSL is an open source protocol. It's an app ecosystem. It enables streaming, synchronization, and recording of multimodal data streams in research and commercial settings. And it's been broadly adopted as a de facto standard with over 100 commercial devices across more than 22 categories already supported. The LSL hardware interface apps and plugins are typically either community or vendor contributed. And increasingly, LSL is directly integrated into OEM device software. So here are some of the devices that are supported by the lab streaming layer. One other thing is that scalability and automation and replicability are very important for BCI research and development. So we've been building the Neuroscale Insight service to address this. And the way we do that is by providing standardized configurable workflows for end-to-end data analysis and machine learning model training and interactive graphical report generation for either individual data sets or for entire studies. And the automated workflows we're using currently span quite a few different sensor modalities and also include conventional stats modeling as well as BCI modeling and classification. And we're also working with leading sensor hardware companies like CGX and Nyrex and others to fully streamline the workflows so that it goes from like turning on the hardware through running a protocol to visualizing the results in a variety of different graphical and standard data formats. So if we want to say like analyze data or train a BCI model or a set of BCI models from a whole study's worth of data, we can actually upload our data to the Insights cloud platform. And then we can run one or more pre-built pipelines that we can quickly configure to match a specific data set or hypothesis. And then finally, we can generate study level results across groups of individuals or repeated sessions and such, including machine learning results. So in this example insight report here, what's called the frequency band CSP supervised machine learning model which is a pretty standard model for BCI, is applied to a task where a person has to kind of quickly inhibit a motor response, and then we try to classify that. And this kind of model is actually biologically interpretable. So it identifies neural features that carry information about response inhibition. Here I'm just circling a few like frontal midline theta, right frontal motor mu, posterior alpha, right frontal beta. And then we can look at the time frequency profile of these different components and observe a significant increase here in beta power that's associated with successful inhibition. And this is also visible at the level of each single trial. So there's like a real-time capable decoder for whether or not you are successfully inhibiting a response. So whether or not you're exerting good cognitive control. And then an important practical question is also how to produce BCI models that can generalize across individuals or contexts or different interventions, even hardware systems and other factors. And of equal interest is the personalization of models to individuals or subgroups of a larger population. And both of these can be achieved with standardized methods for data representation, event and context description, and data processing. And we and others have been working towards this for some time. I've listed some of the recent papers down here on mega-analysis of EEG activity. And that's basically the process of like jointly processing raw neural data from many different studies to identify generalizable neural correlates of cognitive state. So the example here shows different clusters of cortical EEG responses to a set of experimental and behavioral events. But this is jointly analyzed over hundreds of thousands of events from 16 different studies at 4 institutions. So this is a TSNE nonlinear manifold learning approach here, just to identify those clusters. So in closing, I'm just going to quickly highlight 2 recent BCI research projects that use deep learning to sort of give you a little sense of where some of the research sits. And the first is a NSF-sponsored project that has the goal of enabling accelerated acquisition of reading and other learning skills using hybrid BCIs. And a hybrid BCI combines one or more different sensors and fuses them to decode a neural state. So as part of this project, we designed a multimodal deep learning approach to try to classify whether a participant understood a given sentence. And the model fuses EEG and gaze and semantic NLP features, natural language processing features, to get word and sentence level comprehension scores. And then we use the Zuko EEG and eye tracking data set here, where subjects are presented with sentences like the one that's shown here. And then later they're asked whether the sentence contains a specific relational type. And then we get fixation and pupillometric data and fixation locked EEG features. So the brain response is locked to the eye movements. And those are combined with other features in a neural network model. And then using a 24-channel EEG subset plus eye tracking and with this neural network approach, we're able to classify reading comprehension across 11 subjects with a respectable mean area under the curve of 0.767. And importantly, this is a zero training cross-subject model. So it's basically cross-validated by holding out, a subset of subjects and trying to predict the remaining subject. So a number of the subjects here had AUCs above 0.8. The median AUC was nearly 0.8. And interestingly, we also found that if we included semantic representations of each sentence using what's called an Albert vector embedding, then the accuracy increased to 0.881 AUC. And this could be a little inflated by some aspects of the original experimental design, but in general, this shows a lot of promise for future hybrid BCI approaches that fuse neural and physiological and even contextual features like speech or text processing to infer cognitive states in settings that are relevant to kind of real world applications. And this second project here is one that's ongoing in collaboration with the Institute for Advanced Consciousness Studies. And the goal here is to develop real-time BCI methods for quantifying meditative state. And as part of this project, we developed and compared a bunch of different metrics for characterizing distance between non-meditators and expert meditators from different traditions. And each of these are performing like alternating blocks of instructed mind wandering or meditative and breath focused tasks. And then using Neuroscale Insights processing pipelines, we first replicated some of the findings from the original authors that look at alpha and broadband gamma power differences. And we did brain mapping to sort of localize responses and find significant differences in brain patterns across the meditators and non-meditators. But then for the machine learning part of it, we applied a realistic cross-validated machine learning paradigm where we train a model on mind wandering and meditation data from expert meditators, as well as mind wandering data from non-meditators. And then we have a new person that comes in with no meditation experience. We pull that data in and then refine the model using just a few minutes of baseline mind wandering data. And what we're able to do then is track the novice's meditation distance score, basically looking at how similar their state is to the experts meditating as the novice attempts to enter states that are closer to meditating. So we're sort of tracking the distance of a novice in terms of their brain state from an expert meditator. And this can be done even in real time. What we found is that we could correctly identify when they enter those states that are more similar to expert meditators with pretty good accuracy. Using a time-varying deep neural network approach, we were able to classify the mind wandering versus the breath focus states in the novice controls with an average AUC of about 0.8. One thing to note here in this figure is that as the novices go deeper into the breath focus task, their states become more similar to that of expert meditators. That's this trace here, the breath 2. But that's not the case during mind wandering. So that's a nice validation that kind of as you go deeper into that meditation, you're becoming, when a novice is doing a breath focus task, their brain is looking more and more like an expert meditator. All right. So, so what I presented here is an overview of different brain-computer interface technologies and the role of machine learning and AI in this field. And I've also described some of the efforts that our group has done at Intheon and others to accelerate real-world BCIs through platform technologies. And at Intheon, the goal of our platform is really to support all of the types of applications that are mentioned in this talk and to catalyze growth and innovation in neurotech. And in doing so, to help accelerate translation from the lab to transformative applications in everyday life. And I'm just acknowledging here our collaborators, some really amazing team members at Intheon who have worked on these specific projects that I've shown, and of course the funding organizations who support the research that we do. And I will leave it at that. Thank you.
So Todd, I guess we'll just jump right into the fireside chat session.
Yeah, just go for it.
All right. Yeah, first of all, thank you, Todd, for inviting me to do this fireside chat with these two brilliant and very impressive scientists. And full disclosure, that this is also the first time that I listen to the presentations. So I'm learning with you guys in the audience and really excited and impressed by the presentations. And also for disclosure, I don't have a no PhD, no super strong technical background. So I'm going to bring the IQ level down to the average. So my first question is a non-technical question, which actually I'm very curious about, is what, both of you have brilliant academic track record and background. What made you decide to focus on the specific subject that you focus on? What excites you the most? I think for you, Dr. Wei Gao, is specific wearable sensor, but at a molecular level. And for you, Tim, that is BMI or BCI, as you mentioned, which I think most people think is pretty new, exciting, cutting edge technology, but actually existed for a long time. So just wanted to talk broadly, what triggered you to focus on this specific subject?
Yeah. So for me, I think healthcare is everyone care about. Of course, it's a big topic, and from my experience around me, I feel how to identify the dangerous or severe health condition earlier is really life-saving. So that's why I really want to work on developing some devices that can really contribute into people's healthcare, and especially toward at-home use. And because not everywhere has the resource to go to a medical center, especially in the rural area. I was born in a small village, actually, in the county area. I was thinking, if we can have the device that can perform at-home health monitoring, would be very useful. In this regard, the wearable sensor is the key aspect. And when I look at what is available right now on the market, right, like over the decade, we see different kinds of smartwatch from monitor heart rate, and now they can do more and more. But still, we see the major gap. How can we really monitor chemical molecular biomarkers? There are tons of these biomarkers. None of the technology available right now, none of the non-invasive technology commercially available right now. So that's why we decided to move into this area and stay in this area. I try to make more contributions to personalized medicine.
Great, thank you, Dr. Tim?
Yeah, so for me, I think I'm really motivated by the possibility of expanding human potential and flourishing. So when I think about what it means to be human and this journey that we're on as humans, technology has played a role in that since kind of the birth of civilization. And one aspect of where technology is heading increasingly is towards the technology of the mind and what it means to be able to expand the limits of our conscious experience, to be able to even change our experience in fundamental ways that could give us truly new ways of thinking about our place in the world, being able to address things that even Dr. Gao talked about, like mental health issues, for instance, really addressing the root of suffering in a lot of important ways. So I actually see that brain-computer interface technology provides a really interesting, it has a really interesting role to play in that specific category. And there's also a lot of ways that it can go that don't serve that, but that's my motivation, is to try to take the cutting edge of this technology and really try to understand how to expand the potential of the mind.
Beautiful, thank you, Tim. Now I have a specific question to Dr. Gao. As you mentioned, right, there are not that many companies actually solve the question, a problem that you tackle, which is the biosensor at the molecular level. So with your technology, I know the presentation today is very much focused on measure sweat. So are there other parameters or area that using your technology together was really, really interesting, the basically self-generated power source? Using those two combined technology, do you also measure other parameters other than sweat, or are there something in the pipeline that you can tell us?
Yeah, so as I said, we focus on wearable sensor, which is also one aspect of, in general, like a telemedicine sensor or like a biosensors. Our biosensor technology actually can quantify this different type of biomarker or analyte level in different sample matrix. This could be sweat, could be saliva, could be urine, and we can also develop implantable devices that can do the continuous monitoring inside the body. And also These are, I even mentioned we did even recently the SARS-CoV-2 rapid plex, the COVID-19 diagnosis, the platform, which is the platform can be used to analyze these virus antigen, antibody, and inflammatory biomarker in saliva and in blood. So really our goal is really on the medical side, the telemedicine sensor, portable sensor that can quantify the biomarker level in different body fluid in a rapid way without a well-trained professional. That's our main goal. Of course, this can be kind of like more applications in environmental and defense-related applications, as you can imagine. For example, like a pollution monitoring, the heavy metal monitoring. So we're doing sweat. We can also apply this into the environmental samples, like water, let's say lead contamination. We can easily detect. These are some examples. Yeah.
Yeah, I think there's also, just to follow up on this topic, since we're on it, there is a question from the audience about whether the biosensor technology can be used to detect cancer or other conditions that are initially asymptomatic. And a lot of companies working on early cancer detection using blood, sometimes using urine. So we'd love to hear your opinion on that.
Yeah, definitely. I think early detection, that's basically the main goal for wearable sensor. Our purpose is not really for therapy initially, right? We want to really make prevention. To wear the sensors at home or in a daily setting to monitor our parameters to identify the problem early, mostly before it becomes symptomatic, right? Let's say a simple case of diabetes. People live healthy. Like you see, as people grow up or as aging, right? Like the glucose level can turn higher and higher. That's why in elderly, diabetes is more and more common. But this, if you have a sensor to monitor this, you can identify a problem early. When you get close to pre-diabetes, for example, in California, I saw a report there's 47% adults has pre-diabetes. So that's a major population. How to really make sure this pre-diabetes not turn to diabetes? If you have a sensor to monitor these and to give people advice about nutrition, and to especially if you change lifestyle, you can reverse this trend. That's ideal. For the cancer, is the same. We have a lot of collaborators. They are working on population sciences, like public health. Many are cancer experts. They also focus on prevention. They design different type of a diet, standard diet, and how to control nutrition, nutritional intake to really minimize the chance for developing heart disease, developing cancers. I think that's also main application of wearable sensor, to really look at the biomarker level before it turns to a better situation. I would say when you see these changes, you give people early warning for timely intervention.
Thank you. Absolutely.
One
I guess
on that. I'll just insert one short
sorry,
comment. Totally fine. I think that's a really, really important point, this idea of sort of the early warning and preventative diagnostics. It's also an area that neural state decoding can be very useful in. An example of that might be, for instance, if you take certain kind of mental health conditions, like say burnout, for instance, which once you slip into that state, it goes from being, perhaps more something that you could address psychologically to really a critical physiological imbalance at some point that is really hard to get back out of, a neurophysiological state. And so if you could determine early on that you're trending in that direction by looking at how different networks and systems in your brain are functioning, then you might be able to prevent that from happening. And so we were working with NASA on some of these projects, with the Mars 2030 initiatives, for instance, with people in these isolated and confined environments. And these crew members are stuck in these simulated lunar and Martian habitats. And the goal is to try to understand, can we predict, using these kinds of neural methods I talked about, what their performance will be in the future? And it turned out there was some useful information that we could obtain there. So that kind of lends promise to this possibility on these long missions to Mars, and 3 years long missions where you don't have access to support if something bad happens, that you might be able to detect much earlier than when things become really critical, if an issue is coming, and then head it off at that point.
Awesome. Thank you, Tim, for chiming in. And again, definitely want to make this interactive. I have one more question for Dr. Wei Gao, and then I'll come to you, Tim. For your technology, do you see major competitors in the market or in the industry also doing similar things?
Yeah, of course, in academic field, when this is becoming a rising field, and many researchers become more and more interested because also certainly because of high promise for continuous and non-invasive health monitoring in people's daily activity. So right now, I know like there are major players in like or the IT company, or especially this telemedicine or mobile phone or smartwatch. In general, this like a few the major players, they're all very interested in developing these sensors or device or integrate more this chemical sensing module onto the platform. But again, there are a lot of challenges. That's why right now they are not really commercially wearable, chemical sensing yet. I wouldn't say there is a major real competitor. I would say there will be a lot of collaborative opportunities between the academic and between the industry. So the advantage really, we can explore a lot of new material chemistry to make sure we can solve many of the bottleneck from the sensor point of view, how to design reliable sensor, how to demonstrate early proof of concept, which is the main like promising direction to go. When technology become a little bit more mature and we do pilot study, the industry members or partners will jump in to really bring this to the market, right?
Thank you, Dr. Gao.
Thank you.
Yeah, Tim, one question for you. And you and I chatted before. BMI or BCI, you told me that it actually in existence since you mentioned 80s, 70s. But for a lot of people, even people like us in the industry, I think the common sense or consensus is still that is in its initial stage. Two questions on that. Like, do you see any major big players that are already have mature commercialization application? Second is, if not, or if the industry still, despite existent for a while, but still in its initial phase, what are the challenges and why is that?
It's a very good question. So yes, the earliest brain-computer interface technologies go back to like the 1970s. 1973 is when the term really came into being, although it existed as a concept before then, even as early as the late 1960s. Like many things that we create technologically, there is a long incubation period from invention to widespread adoption. And those barriers sometimes are not merely technological, they are sociological, cultural. They are finding the unique way in which a technology adds extraordinary value without requiring people to completely reorganize their view of the world. So a traditional BCI from the 1970s would have been horribly impractical for somebody to use today. And in fact, it was only really in the last decade or a couple decades max that we've started to see the trend towards more wearable, pervasive, ubiquitous BCI technologies that could be actually worn, daily with a decent amount of comfort. And that's starting to then allow for a lot of new data to be acquired that gives us a deeper understanding then of how we can decode neural states in the real world. So what's happened is there's been even though the technology has been around for a long time, there's been a real shift from just purely clinical applications in fairly limited lab contexts, these kind of widespread real world applications. Now, in terms of which companies are already like massively commercializing this, well, probably the biggest headway has been in the clinical space, and in some cases with implants, with stroke rehabilitation, for instance. There are companies that have raised, upwards 100 million or more to try to address stroke rehabilitation with BCI technologies like MindMaze, for instance. And then you've got big companies weighing in on this, like, you've got famously Neuralink with their neural implant solution, Facebook famously stepping into this space. Control Labs, that acquisition is a brain-computer interface technology on the wrist. Then you've got kernel, for instance, another 100, 200 million, or it's about 120 million, in funding, and many others actually that are we're starting to see pretty sizable venture rounds focused on this specific space. So what I expect to happen is over the next 5 to 7 years, there's going to be kind of a flurry of companies that have the capital to actually start to build realizable products. And the science is mature enough now, I think, to start to really take this out of the lab and into the real world at scale. But it's still early days. So we're kind of in the neurotech space where we were in the computing era in the 1950s or maybe early 60s. But imagine if you could have been there then in the 1960s and known what was going to happen with computing technology only 30 years later and how it would completely change the world. You would want to be doing that. And that's where we are today with neurotech. And it will change the world in the next 20 years, fundamentally. That's awesome. I don't know whether there's any venture investors in the audience. This is very interesting space. Follow up on what you said, Tim. What about regulatory? Now you said that the science finally caught up, and then in the next couple years, there will be a flourishing of companies. But did the regulatory framework catch up at the same pace? I think you and I chat a little bit about medical device as software as a medical device. That's a new kind of framework from FDA. Can you just comment a little bit on the regulatory framework for the industry? Sure. Yeah, I think that, of course, many brain-computer interface technologies are and will not be regulated because they're either consumer technologies or they are in the wellness space, which currently the FDA broadly doesn't regulate. So I think you'll see a ton of applications, like for instance, a BCI that helps improve your stress would be typically unregulated as long as it's not trying to treat an indication like clinical anxiety, for instance, right? On the other hand, what the FDA is looking towards is trying to accelerate a lot of the things that BCIs rely on, like, for instance, the ability to incorporate AI inside of a diagnostic or therapeutic solution. So we're already starting to see the first AI-driven diagnostic systems getting FDA cleared. We're also seeing interesting, you mentioned like software as a therapeutic software, digital health solutions. Achille Interactive recently got the first FDA clearance for a digital therapeutic that's a computer game that addresses ADHD, for instance. So when you look at, what the FDA is trying to do to kind of innovate and really change the framing to keep up with the modern technologies, you can definitely see a way in which BCI technologies will get faster clearances as the FDA makes those shifts. So yeah, fingers crossed that the regulation can stay up with the pace of the technology and yeah. Thank you, Tim. Next question is addressed to you both. Dr. Gao, I wanted to bring you back to the conversation. Mental health. COVID has brought mental health front and center to a lot of the discussion and research. I think both of you addressed very specifically about how your technology could be applicable to mental health. I think Dr. Gao, you mentioned measure stress through sweat. I'm sure there are other biometrics you could measure stress too, and you mentioned 95% of the disease is stress related. And Tim, you mentioned really fascinating. I think there's a question from the audience as well about meditation. I'm a big meditator, and I think in this space, people are struggle to measure, to quantify how meditation actually change people's brainwave, and seems like your technology could change that, could actually quantify that. So my question is actually very broad. How do you see the kind of future of mental health? How does your technology play a role in shaping the future of mental health for mankind?
Mm-hmm. Yeah, as I said, stress and mental health is one of our main focus because right now there is no good way, especially for at-home use. You can imagine, a lot of people have depression that don't know they're depressed. Like, of course, stress could be bad, it could be good. It's related strongly to human performance as well. So I showed some example. We can monitor stress hormone. There is a couple, like a stress hormone, a number of stress hormone actually in our body we can monitor. And importantly, like, like there are many smart watches, they claim they can also do like a stress monitoring by monitor the EEG or heart rate. I mean, like these different vital signs can also be used. And we have a collaboration with NASA as well to monitor the deep space stress and mental health. Our goal is really incorporate our novel wearable chemical sensor together with the existing physical sensor. Then we have this multimodal, the entire multimodal wearable system. They can really quantify, collect all this physiological information, including vital sign, including chemical biomarker. And we propose also using machine learning to analyze the data to get classification for stress. Of course, we can certainly do depression as well, because it's just how we run machine learning to classify this. We think that this will be very important. This could be a promising solution, not only our own technology, but in general, the vision, like a multimodal sensor coupled with machine learning, which can play an important role in stress and mental health management down the road.
Totally agree with that. And I'm glad you brought up UN mental health, because I think, again, it's really important to think about how these technologies are really helping to serve an unmet need. And that is an unmet need. In the US, there's over 5 million patients with drug-resistant serious mental illnesses who could benefit from a BCI. There's far, far more actually who are not being well served right now, simply because it's extremely difficult to develop pharmacological solutions that can precisely target these systems and address mental health. So, there's over 40 million Americans who suffer from clinical anxiety disorders. And the typical response rate to an anxiolytic therapy first-line treatment is 50%. So if you think about it, that's about 20 million Americans and growing. COVID, grew at something like 620% or something over COVID, the number of clinical diagnoses for anxiety, and something like 800 for depression. So just this incredible unmet need that we have a burden to serve. And when you think about what everything that Wei has said is totally true. The multimodal approaches are absolutely the way to go. Very excited about the work that he's doing. When we think about how we change the state, that's another piece of the equation. So what BCI technology allows you to do is not just read from the brain, but write to it. So with neuromodulation, which is the ability to put energy specifically into circuits of the brain, you can develop ways of changing a brain circuit to alleviate a mental concern at the same level of efficacy as a drug, or sometimes much, much, much higher efficacy. And so this is really exciting, because it means we may have a potential way to adapt a therapy to an individual and do that without side effects that drugs present and without the cost that drugs require. That's not to say that pharma is not a great solution in many cases, but there, again, are many people that it just will fall off the pipeline there, and we need to help them. So I think it's a tremendous opportunity, actually.
Yeah, and Tim, I just want to chime in there too, right? And using BCI, it's also personalized, right? So basically you can design different treatment based on the results of that individual. So it's one rather than a very qualitative approach.
I mean, you can almost imagine it as if you took a smart pill, and that pill, the moment that it went into your body, was adapting itself to release just the right amount of the dose of the medicine, and then it shut itself off. And then not only that, but it also learned your brain system and adapted its own chemistry to you. And to some extent, that's what a closed loop bioelectronic medical solution attempts to do. It just does it non-chemically. It uses, generally energy transfer directly to the neurons or to the nervous system. But it's it's still early days for that too, but it's very, very exciting.
Yeah, absolutely. And I think the other thing that you mentioned that I want to add on to is along in America, there are so many unmet needs for mental health. But if we think about the rest of the world, emerging countries, they are not even basic condition to diagnose, diagnosis for depression. I'm originally from China, and just to think about like rapid rate of development, how much stress that could put on people's brain. So definitely applaud to both of your research on that. My last or two or one question is also COVID kind of like a accelerator and facilitator in a way for healthcare industry. And we see a lot of large technology companies and consumer companies actually jumping into healthcare. It almost like the border between clinical side healthcare company to consumer companies that become less clear. What I meant by it is probably in the future, the largest healthcare company would be Google, be Apple, be Amazon, and Walmart, because everyone is going into healthcare. So just giving kind of, that's my observation, that consumer company and clinical companies, they're intersect in healthcare, especially when this shift happened from treatment to prevention. So when you design your product, how do you kind of think about that trend? Do you design product for both consumer market and clinical market, and there's different costs, different regulatory implication? Sorry, this is a very long-winded question, and I hope I make myself clear. How do you deal with that?
Yeah, I think they are connected. Even from our research, they are connected. We develop a device, we develop a sensor, they can collect data. How to use the data, that we decide, like it's a consumer product or FDA approved medical device, right? It's like a Fitbit. If I only read my heart rate, that's more like like a consumer product, right? It could be informative, but I don't use it for medical diagnosis. From technology development point of view, initially we are doing the same thing. We want to develop the best sensor, reliable like a sensor to get accurate data. This can be useful, can be informative for the user, and also if it's accurate enough. And they also, like as I said, many applications, real applications, specific application can be linked to machine learning as well. As our algorithm developed, if we can predict a certain health condition or diagnosing a certain condition or directly give user advice what to do, intervention, then I mean it became a medical device, right? I think they are really closely linked. That's why all these major tech giants, they are interested in both, right? Technology-wise, like Apple Watch. Apple Watch can be a medical device as well right now.
Yeah, I resonate with that. And, I mean, the big tech companies have, of course, made plays into this space. I mean, famously, Verily, which was, one of the alphabet companies, Google's, play at sort of massive big data approaches to addressing health. You can see fingerprints of that on many other companies out there, like, my friend Brian Pepin's company, Ruin Labs, that is, trying to aggregate and organize a lot of data to identify good neuromodulation targets. So you can see how that could not only be useful for that data for clinical applications, but also for consumer applications. If you know what circuit to nudge to, change mood or brain function. So there is this increasing interplay, and the lines are blurring. And I think it goes back to that point, Yiwen, too, where you're talking about like digital therapeutics, and when you have a game that is a therapeutic that is FDA cleared, it really conceptually seems to blur the line in sort of like software as a therapy. And so being able to cross over between companies that are traditionally consumer companies or app companies, and now they can be medical device companies because they build a therapeutic app. That potential does exist today already. And I definitely think the big, tech giants are certainly looking at that very carefully, certainly on the data side.
Got it. Any concerns, since we're talking about AI and mega amount of data, is data privacy a big concern in the industry when you develop your product, like, the ownership of data, is that a concern that you need to address?
I think certainly. I mean, data privacy, security, it's a big topic. I think we have many researchers working in this field. I think definitely this is one of the important aspects we have to pay attention to when we wear more and more sensors and more how to protect this data, how to deal with this data. I'm not a data like a security or protection expert, but I do think this is a very important topic we have to pay close attention to. And the user will be very careful with this. They care a lot as well, right? As you can imagine.
I agree. This is like absolutely essential that we get this right at the early stage of developing these technologies. So, you know, we can think about, we're actually blessed by the fact that we're in the early stages of this neurotech wave, because it does allow us to look at the lessons learned from the information age and what we thought might go right, but ended up maybe going wrong in a few different directions, and how we can architect systems that from the ground up are built to preserve things like, you know, privacy if you wish it, or autonomy and agency, you know, the ideas that are kind of central to, in many cases, to our concepts of human rights and mental rights. And I'll just note that there is something called the Columbia Neuro Rights Initiative that is focused on trying to create almost a legal charter, basically, for how companies can proceed virtuously when they are going into this space. And BrainMind is another a great organization that has a neuroethics initiative that is also targeted exactly this point.
It's really great to know. Thank you. Last question, and then I think there's some questions from the audience in the chat box as well. But last question from me is super exciting stuff you're working on. Looking out for 10 years, other mega trend or other interesting opportunities that pick your interest that you might work on next, or you know you want to talk about?
I think I have a strong interest in what kind of our team is working on also, like how like human machine interface, right? Like how our sensor data interact. I mean, like with the human and also with the robot. And I mean, overall in our lab, we also working on the direction of human-machine interaction. Just like how also we involving with machine learning, how like for example like rehabilitation, and also like random prosthetics, all this how the sensor data can be help for developing next generation robotics, also for medical care, of course, and beyond beyond healthcare as well. That's something I'm very interested in as well.
I'm likewise very interested in what Wei is doing, so maybe we should collaborate. But,
yeah, you guys can co-found a company.
Well, I think what is really, really, really important and really exciting is about how we make the technology disappear. So, you know, the sort of stuff that like Wei's lab is doing to try to have these systems be small and efficient, like the idea that you can have a chip that is powered by your sweat is incredibly important, because the power supply is like one of the biggest problems in like why your systems are big and bulky and you have a wearable that's, you know, not invisible. So once you can do these kind of sweat powered things, you can have subcutaneous sense and stim systems that are, you know, just existing as part of your body. And when that disappears, it really does enable a big fundamental shift in the way that people can adopt these technologies without stigmas, without certain kinds of challenges. And it really opens up the democratization of it too, I think, in a lot of ways. So I'm really excited about that. The other thing I'm really excited about is just what we were talking about earlier, things like mental health, neuromodulation, human flourishing. You know, someone asked about meditation. I've been meditating for a long time. I'm super interested in what is happening in meditation. There are some really fundamental things happening in your brain and physiology. And can we accelerate that through technology is a really interesting question. So, you know, stay tuned. There's some very exciting stuff happening in this space, but yeah, it's all early days. So it just feels like it's a good time to be in this space.
Right. Todd, I think in 3 years or 5 years, we'll have to have a sequel of this dialogue. Maybe they already co-founded a company by then. If we still have time, there are some questions here that I want to address. Okay. Question for Professor Gao. Have you considered application to ecology and biology through using biosensor tech to monitor larger population of animals? Yeah, I want to ask that question too.
Yes, certainly. We have interest. Certainly, just we don't have enough energy to do everything at once. But I can see that this wearable sensor, actually, they're not only wearable for human. I saw, in our field, people working on the wearables for plants. Just you put this on plant, you can monitor all these nutrients, gas molecules. It's just more of biology, ecology, study. And we are also doing, and many other people in our field are working on developing the sensors. Just developing the sensors that can be implanted in the animal. We are working with like a mice and rats, and some of these can be with the pig, different animals we are working on for the implants. And actually, there is another professor working on the insects. We are thinking about developing some device that can, be like carried by small insects. We can study their behavior as well doing the sensing. I think that's definitely biosensor will have broad applications, not only to monitor human, as I said here, animals, plants, enormous applications, I would say.
That's super cool. I love that. In my space, by the way, it doesn't have much of a practical application to plants or animals as much, but incidentally, the use of like EEG type technology on plants was attempted back by some clever Russian scientists back in as early as the 50s or earlier. And there's a lot of interesting papers on that are maybe not most immediately useful. But I really love this idea of that this type of technology can help us to develop healthier ecologies, the continuum between humans, plant life, animal life, and how a single core piece of innovative technology can help to kind of bridge the gap in a way that helps us to fit better into our ecologies and help to have more sustainability, for instance. That's super exciting.
Yeah, Tim, I wish you can meditate my cats so they don't. So to you then, Dr. Mullen, what do you think about possibility of using the Neuroscale technology on multiple people simultaneously to help them synchronize their actions, such as dancing?
Oh yeah, we've done that. Actually, the largest number of people we recorded the synchronous neural activity from was almost, it was like 710 or something, it's about 700 people across the US, in LA and New York. And they actually controlled the brain-computer interface together in real time, like played a mental tug of war with like 400 people in one city and 300 in another. So these things are achievable. Modern internet technology, obviously, if it enables you to tell your Tesla to turn on, from your phone when you're anywhere else in the world, you can send brain data anywhere in the world and have it synchronize up with other data. But one of the things that this is speaking to that's actually really interesting is the idea of things like team flow, and the idea of getting into kind of a group flow state. And this is something I have worked on, and colleagues of mine have worked on a lot. And there are some interesting biomarkers for this particular type of state. And interestingly, some of those markers are pretty similar to what we see in meditators who are engaged in deep levels of meditation. So there may be some interesting parallels there between what's happening when you're in that coherent group flow state and what happens when you're individually in that deep contemplative state.
Yeah, Tim, I think there's a book called The Flow, where you're in that flow state when you're very, very focused. It's almost like you're meditate, but you're working.
Yeah. So there are some, there's, it's a little reductive to call it the same thing as a meditative state, and there's so many different types of meditative states. But there is an interesting continuum across these states, which really involve how you are modulating the circuits of the brain that construct the sense of self. And so we now are knowing more and more about what circuits in the brain, like the default mode network, and how that is playing a role in the construction of self. And then, when you can start to track that and maybe even shift it through feedback, you could potentially get people more into this state where their self kind of disappears and they connect to others or even to their environment in a very fluid way. And that's kind of what it feels like to be in a state of, perhaps a samadhi.
Yeah, I think there's another question, maybe you have already addressed it, is is there any study has been conducted during long meditation retreats? And I am going to hijack that question and ask something a little bit controversial. Have you also done any study to study the actual clinical or actual effect of psychedelics to the brain?
So the answer of the latter is yes. And there's actually a study that was conducted back at UCSD many years ago. Actually, my interaction with studying psychedelics goes back to Berkeley, where one of the first studies that was using MDMA as a therapeutic was approved. My friend Matt Baggett was doing that study, and I was introduced to that work at that time. But the use of things like MDMA, psilocybin, for instance, as a therapeutic has a rich history. It's very complex, a lot going on. But recently, there's been a huge shift into a recognition of the enormous potential therapeutically for some of these psychedelics. And so EEG and BCI technology is actually playing a really interesting role there. You might know of Atai Life Sciences, for instance, which is a psychedelic medicine company, now a company, you know, they've been exploring, like acquiring companies that are doing neural interface technology work, for instance, like cyber. So you can start to see a combination, a fusion of the ability to have psychedelic interventions that shift your state in profound ways, but then the ability to monitor that shift using neurotechnology and then allow you to titrate the dose or figure out what the right, you know, therapeutic component should be or the right intervention to make sure that somebody gets the maximum benefit without, you know, the side effects that might come from such a big state shift. So yeah, there's a lot of active work going on that now.
Wow, absolutely fascinating. I think we still have some time. Please, if there's more questions, please put in the chat. I want to go back to the first one that is addressed to Dr. Wei Gao. I'm interested in how trauma survivors undergoing treatment sweat can be used as a measurement of their recovery.
Yes, certainly. I think for the not only trauma, right? In general, for the therapeutic process, we can look at in general the biomarker changes over time. Look at the inflammation. Look at like all these trauma-related biomarkers, and I also want to emphasize that, you know, not only the wearable sensor, we can monitor the entire recovery process. I didn't talk in my talk. We can also help the medication personalization. You know, like not really related to this, but you know, for many like chemotherapy, those people based on certain like a range, right? The range could be very narrow, too high, too low, not good, both not good. People have to come to the clinic to do blood draw to look at the point value, which change very quickly the drug level in the body. And with this sensor, we can personalize the therapy as well to make sure the physician will know how much dose right now in your body, and not only look at the biomarker level during the recovery process, but also helping this therapeutic process by self-guide to achieve the drug dose personalization.
Great, thank you. I think we have run through all the questions. Any more questions from the audience? Looks like no.
Yes. Can I ask a question?
Please. Okay.
You're muted.
Jose, you're muted.
Oh, should now I'm not muted. Okay. So I was a bit late, so I don't know if it was discussed, but it's a question for Dr. Mullen. I don't know if you know the work of Tom Mitchell at CMU. He has this really cool system that you could basically tell which words people were thinking. Have you found any kind of, I don't know if I haven't followed up that much, but is there any interesting application of that you can do or think about that?
Sure.
You can put a link on the
so the
chat.
work like Tom Mitchell's work and also like Jack Gallant's work at UC Berkeley is in that same kind of vein of using, you know, these sort of large scale machine learning models to try to, you know, you kind of invert these models, and then from like fMRI data, you can make predictions about what basically the person experienced, whether they saw a particular image or whether they heard a particular or thought a particular word. So this is certainly a really fruitful area. It's exciting and interesting. I think some of the challenges there are going from like generalizing outside of the data set that a person is exposed to, as one example. I'm not saying that these experiments have not attempted to show the possibility of doing that, but that is a challenge. So, if I show you, let's take like an experiment where I show you, thousands of pictures or images of different categories. I look at your neural responses. I then train a machine learning model to basically make some predictions about what images you saw. And then I can take a new person and look at their fMRI data, and I can show them an image, and the machine learning model is blind to the image shown. It says, oh, I think it's probably this that the person saw. That the ability to generalize far outside of the data sets that were presented to a person is one of the challenges. Same for like speech. I think some of the really exciting work in speech reproduction and sort of thought translation devices have been carried out by Eddie Chang at UCSF, who puts small microelectrode arrays on the surface of the cortex. And these are, like small, like 400 micrometer EEG electrodes, you can think of them as, but they're underneath the skull, and you put them over the motor portions of the brain that are responsible for speech production, as well as the auditory cortices. And he's actually shown the ability to be able to classify like individual phonemes that a person's imagining, produce words and sentences. So I think that direction is particularly exciting for sort of real, potentially fluid speech prostheses that just allow you to think a word or a sentence and it's produced. It's still a bit early days, and you need a surgery to have that particular approach applied. So it's not for the general public at this time, but that's definitely a direction that is very exciting.
Yeah, thank you. No, I thought it was pretty cool. I know in the real experiments they could just basically recognize concrete nouns. They had a hard time with things that were like abstract, but it was like a dog or the picture of a glass or things like that. Those They could classify better. But if it's something like some abstract, like peace or some abstract concept, then they couldn't do it.
Yeah.
I know they did some follow-up work we're trying to see when different kind of aspects of language comprehension appeared and when they were presented at board. And there was a timing aspect in which first they would like count basically they could time it, and it was, I think, PET. It was not like an MRI. It was some other imaging technique that was faster than MRI. But they could say when it seems at the beginning, going from memory, but it recognized like the size of the words, how many letters, and then they could begin to different parts of the brain would light up that would correspond to more semantic concepts. So it's like a temporal hierarchy, and that was also fascinating.
Yeah, and actually, referring back to some of the work that that we were doing at UC Berkeley in Bob Knight's lab, this was actually really Ryan Canolte's work and others with these implanted electrode arrays, some of these same kinds of things you're describing, where there's a propagating pattern from areas of the brain that are involved in like low-level phoneme, decoding and reconstruction, to higher order semantic areas, to frontal circuits, to production areas. There's this loop that happens, and it happens very quickly. It's over like, less than a second. You get this propagating pattern as the information is being propagated up to other regions of the brain that are more perhaps interconnected with other abstract reasoning centers of the brain. And so that's not unexpected that you would see that kind of a time course going from kind of fine granularity to more abstract representations. Important to recognize there's a lot of feedback too, or kind of top-down information sets context. So if I'm expecting to see a particular word because of the context of the words that I've seen, then my brain creates a top-down sort of reinforcement of the low-level areas of the brain to pick out features that confirm the hypothesis that the brain has about what word should come next, right? So you can see it almost the other way sometimes too, where the activity that is primary is the contextual sort of Bayesian inference part of it that is trying to predict what comes next. And that is actually influencing how the low-level sensory systems are processing information. Anyway, that was probably a lot more deep than or technical than needed to be, but yeah, a lot of temporal dynamics going on there.
Cool. I have more comments, but I'll shut up with other people.
Yeah, I think there is one more question about how rapid and significant is the rise of nanotechnology in both of your industry.
Wei, it's probably much,
I mean,
much more heavy than what you're doing.
yeah, I've talked a lot because, for example, I talk a lot about graphene biosensor. Nanotechnology is crucial to develop sensitive biosensors. If you use a bare carbon electrode or gold electrode, it's very hard to detect very low level protein, hormone, or even metabolite at micromolar or lower. That's why we use a lot of like a nanomaterial to improve the stability and the sensitivity of the sensor. When I talk about the biofuel cell, I also mentioned that this nanomaterial is crucial for us to improve the power density we can get. Overall, I think nanotechnology is playing more and more important role in developing novel sensors.
Yeah, and like in my space, it doesn't really feature in like the non-invasive technologies that much that we work with day to day, but it is increasingly critical to the implanted work. So, you know, the material science around, for instance, these like chronically implantable, biocompatible microelectrode arrays or flexible substrates that kind of dissolve and leave extremely thin conductive polymer film behind, like all that requires nanomaterials and nanotechnology to be able to achieve that capability. So yeah, it definitely features in the implant side of things. Interestingly, the kind of dream of maybe the 80s dream of nanotech that is like little micro machines running around, like cleansing your brain and body, you know, that I think is still not quite there, but there is a really interesting promise in the coming decades for even for neural interface technology to be able to miniaturize them down to the point where you could have, you know, even, you know, like injectables, insufflatables, ingestibles that are actually filled with little nanomachines that essentially have the ability to, using maybe some of the technology that like Dr. Gao is working on or other things, to power themselves, to record activity, and to stimulate cells. And
we are working on nanomachine, nanorobot.
Yeah, so that's like super
that's my
cool.
second topic. I didn't talk today, you know. For brain also, some could be, yes.
That's definitely a direction, and I think the first steps towards it are maybe like the Iota Biosciences sort of quote unquote neural dust platform, although it's nowhere near the size of dust yet. But it's really neat because you can kind of like stick these little like, you know, several, you know, 100 micrometer little motes and power them with ultrasound and read the signal back out non-invasively, and they can stimulate and read. So imagine that, but just like 100,000 times smaller, you know, that would be really powerful. Even 1,000 times smaller, actually 1,000 times smaller probably would be fundamental enough that you could scatter these around the brain and read and write to the brain without the need for any wires.
Mm-hmm.
Yeah, thanks, Tim. We have another question. This is, I'm sorry, Beata, you have to go through that. I was just reading it that your late husband is a Caltech 81 and died due to suicide, but his chemistry of his sweat has changed before his death. So is Dr. Gao looking at relationship regarding sweat and between sweat and mental illness that may lead to death by suicide?
Yeah, I'm sorry to hear that. I think, yeah, I do understand it is an important topic. Why talk about mental health? We talk about depression. Actually, my collaborator at the Cedars-Sinai Medical Center, he's an expert about depression and suicide. One of the key justification he put to me also, because that's why we were talking about why the questionnaire doesn't really work well, because even the depression questionnaire or suicide is also based on the questionnaire. If this person wants to suicide, will this person tell the truth or not, right? They will not tell the truth even if you give the questionnaire. So it's really hard to monitor, to quantify this. Our goal is really to monitor this biomarker level to classify depression and potentially suicide. Suicide is another condition, but closely linked to depression in general. Yeah, we are working on that.
No, thank you so much for answering the question. He was actually a protege of Richard Feynman at Caltech physics and in 81. So I heard all the stories. So I just felt And I wanted to ask the question for different reasons. So thank you so much to both of you. Thank you so much.
Thank you. Thank you.
Yeah, also thank you, Beata, for your bravery of asking this. All right, any more questions? Oh, nanorobots. All right, then I think, well, Todd, and thanks for, again, for, allowing me to do this, to conduct this really exciting fireside chat. And Dr. Wei Gao and Dr. Tim Mullen, it's definitely an honor to be here with you. And hopefully in 3 years, you co-found another unicorn. Yeah, and thanks everyone for your time. If anyone wants to reach out to us, I guess at least I can speak about, on my behalf, feel free to add me on LinkedIn or reach out to Todd. And then I'll hand this back to you, Todd. I think you want to talk about the coming AI conference.
Thank you, Yiwen, for your wonderful and masterful, taking us through this journey, through these questions. Appreciate you. Thank you.
Thank you, Tim. Thank you.
Yes, thank you, Yiwen Li. I mean, I also don't have a PhD, so I really appreciate you moderating this conversation with obviously these two geniuses to help our audience understand the future of commercial applications of machine learning driven bioelectronics. And of course, thank you, Professor Gao and Dr. Mullen, for sharing your research and insights on how wearable technologies will help us live a healthier, happier, and longer lives, especially when it comes to early warning detections and preventable care with stress and mental health. And yeah, for sure, I hope we have a reunion talk in a few years to see where Dr. Gao and Dr. Mullen will have their potential collaboration. But yeah, that concludes our virtual talk. I hope you all will join us virtually and in person on October 21st at AILA's Life Summit. You can learn more at lifesummit.la. But yeah, we will be hosting an event virtually and then have a private reception at the new Bioscience LA headquarters in Culver City. And so hopefully we'll get to join, hopefully we'll get to see you in person. But either way, thank you all for your time and thank you for joining us tonight, and hope to see you very soon.
Thanks, everyone.
Thank you all.
Bye, everyone.
Bye.
Bye.